So let's try to take a look at this example and analyze this and see if we can make sense out of this transformation. We can translate this back into a function, a t function. And basically that takes your x and y. Can I use x and y? I use x1, y, x2. But, you know, we can think about this as, since we're going from 2D to 2D, we could just say x and y, if that's okay. Oops, this should be a 2 here. So this is the x vector that we usually use, but let's say it's okay to use x and y. So what we could do is we could take a look at how the transformation works, the transformation that takes your x, y values goes to 1 times x plus 2 times y, and then 0 times x plus y. Does everybody understand where I got this from? I kind of did this dot product, 1 times x, 2 times y. That's the top row, and then the bottom row, it's 0 times x, 1 times y. Okay, so that's how I got this. So this is your linear transformation. And this is the function form of the linear transformation, so that it has an input-output. So it goes from R2, and then this output vector here is also a two-dimensional vector, so that's also R2. So it goes from R2 to R2. And I think these are good to study because they're visual for us. We can see it and do some manipulating and seeing what happens. And what we could do is just run through a quick exercise of following the dots. Like if we have these 4 dots, for example, where do they go in your transformation?
First of all, column vector of the matrix is where is where the x-axis ends up, and the second one is where the y-axis ends up.
X-axis ends up and the y-axis.
So what is being mapped to the x-axis previously is now mapped once again to the x-axis, which is represented by that vector.
Close. I think something like that is close. So usually it's good to try to figure out where points go, points to points. You can actually, technically you're looking at it as a vector. So vector 0, 0 gets mapped into, if you put 0 for x and 0 for y, where does it go?
Back to 0,
0, 0. So rule for linear transformations, we saw this last time, that the 0, 0 vector always goes to the 0, 0 vector as your output. Okay? If it doesn't, then it's not a linear transformation. Something went wrong. All right, let's take a look at another point like 1, 0. And 1, 0, if x is equal to 1 and y is equal to 0, where does this go? 1, 0 also, right? And then now let's take a look at 0, 1. If your map is vector 0, 1, where does this go? 2, 1. And then finally 1, 1 goes to 3, 1. And you can kind of see this mapping with the picture. That's what's nice about being able to see this using a picture, is because you can kind of see where those points go and how they move. right? Yes?
What is this square on the left represent?
Oh, this is just points in the domain and where these points go. We could draw a different figure here. We draw a circle, and we can draw the thing, rectangles or star or whatever. But the idea is that we want to see where this goes over here. And the matrix is a transformation. So, I mean, we can be silly and draw some other stuff. I wonder if I can... I didn't think about this earlier, but let's see if I can do something. There's a way to put pictures here, and I don't remember. Insert. I don't know. Well, I'll put something weird like the sine function. And you can kind of see how the sine function also changes according to the transformation. We could put a circle. And then we can kind of see how that transformation works out also.
What other transformation matrices?
Yeah.
The 1, 2, 0, 1.
Yeah, the 1, 2, 0, 1. That's what's adjusting the thing. See if I can come up with a picture. No.
What about those little like graphs?
Yeah.
The little pictures, they look like mountains. But
Yeah, that's a zoom in and zoom out. Anyways, I'll figure it out another time. So the point is that these transformations do something, and then we're interested in looking at different sort of equations. So I think last time what we were doing is that we're just changing some values for the transformation. Like if we make this into a negative 3, for example, and how that would look like. And if we change this to a positive number, and how things would change if we change that thing. But this isn't the only number that we can change, right? We can also change this number down here. And I think we had a little guessing game as to what would happen if I changed the lowered number here into something else. What do you think? Do you remember what happens?
we didn't do it.
Oh, we didn't do it?
We go skewed in the Y
Skewed in the Y.
and down.
So this thing looks like, if you can try to follow the dots, I try to color code them. So this is a red dot over here, and that red dot got shifted down. And if this was a positive number, then it would just go up along the Y. So it would be nice if we can get a handle on this and on why it's doing this and how we can control our variables and stuff. And what we can do is we can go back to our list of points here, and I think if we know what happens to 2 of these points, then we can get a handle on what else is happening everywhere else. Because there are other things that can happen, right? Let's see. I think I put a -1 here. and then a positive 1 over here. And it did some sort of, not just a rotation, but also a stretch.
And the reason that that your purple and blue dots didn't change with the previous one is because you still had the identity positions as one.
Yeah. Well,
Because if you change those, then your purple and blue are going to move, right?
I don't know. Let's see. Let's change this into a 2.
I didn't think they both move, but it's good to know.
Yeah, so several things happen when we change these things. So this is the red dot. I think this is still the, I can't tell the colors anymore. Oh, it's blue. And then this is purple. Right, so those are those dots that are getting shifted around. Let's make this a negative. So for some reason that jumped to the other side. This is purple. So this is the purple dot right here that got mapped into here. So let's take a look at this one. This is an interesting example. And if you looked at it, the 0 vector still goes to the 0 vector. So that's not even worth writing anymore. Let's take a look at what happens to the point 1, 0 and where that goes. So if we put that here into this function, x is equal to 1, y is equal to 0, what's our output? Is it better if I write the t function? Maybe you can write the t function. T of xy equals what? Negative 3x minus y, and then x plus 2y. So when x is equal to 1 and y is equal to 0, what do we get? Negative 3, 1. So negative 3, 1. So this point over here goes to negative 3, 1, 2, 3, comma 1. Goes to that point right there. Okay, the next one is 0, 1. So when x is equal to 0 and y is equal to 1, where do you go? Negative 1, positive 2. So negative 1, positive 2. That's that new purple dot. So there's also, not only does it shear in a weird way or rotate in a weird way, but it also does some sort of reflection thing.
What's our notation for like writing this out? You put t in front of the 0, 1.
Oh, so right now I have this little arrow notation to say x goes to t of x, but yeah, you can rewrite this as t 0, 1 equals negative 1, 2. So that's the other way of writing this.
No, I mean, it's quicker to do. I'm just curious. My brain.
Yeah. And of course, if this is the matrix A, then it's the same thing. We can also rewrite this as A 0, 1. This is like your x. Ax is equal to minus 1, positive 2.
Right, and like the ones that you're listing on the left, they're like vectors, corners, like their addition.
Yeah. Okay, so I don't know if you can see the relationship between A and T, right? I think we talked about that already. the coefficients, whoops. The coefficients are of the x is like the column vector. Do you see that? -3, +1, and -1, +2. Okay. The other important thing to note is that, notice I also didn't bother figuring out what happens to 1, 1 here. Did you notice I didn't do that? Why didn't I have to do that? Well, one's a red dot and it's already showing.
I don't understand what I don't understand.
Yeah, I don't understand what I'm asking either.
I don't understand what you mean by why did I not need to do this?
Yeah.
You're transforming vector 0, 1 plus 1, 0.
Yes. So this transformation is actually just equal to the transformation that you would get from 0, 1
T,
to 1, 0, right? Because it's linear. And so if you noticed, if we would have added the results here, -3 plus -1, that's -4. 1 plus 2 is +3, and that's exactly where that 0.11 went to. So really, knowing what happens to these two vectors is enough to define your transformation. In fact, do we know what these vectors are called? 1, 0, 0, 1? Basis vector, they're unit vectors, they're basis vectors, right? They're called standard basis vectors. So if we have a handle on the standard basis vectors and where the transformation goes in your standard basis vectors, then we can define our transformation. So I think that's how the next section starts. Yes?
So I can find like any number in that out of just those two vectors.
Yes.
Like just some
With just 0, 1, and 1, 0, you would know where the vector 17, -3 goes to. Right? It's just a linear combination. All right. So this is our key. If you have a transformation and it's a linear transformation, then there's only one matrix that exists that would support this transformation. And that transformation matrix is dependent on these vectors they call E sub j. So the E sub I vectors, E sub j vectors, are the standard unit vectors for whatever space you're dealing with. So in R2, there's only E1 and E2. And then E1 is 1, 0, E2 is 0, 1. Okay? If we know what the transformation does to these two vectors, then we know what the transformation does for anything else. Not only that, but we can easily create the matrix that deals with this. I don't know if you guys noticed that. 3, 1, -2, or -1, 2. You notice? Those are just the columns. Let's go back to the previous example. 1, 0, 2, 1. Those are the columns of the matrix. Okay, so now if we can do a transformation, if we can define a transformation and do it to these two vectors, then we can create a transformation for everything.
This is your dependence from section 1.8.
This is now 1.9.
Oh, yeah, okay.
Just in a more abstract world, in R4 you have 4 of these standard basis vectors: E1, E2, E3, E4. And E1 would be 1, 0, 0, 0. E2 would be 0, 1, 0, 0, etc. So when they say EJ, EJ is just a vector with zeros everywhere except for the jth component, where the jth component is equal to 1.
So you want the columns of A to be linearly independent?
The columns of A should be linearly independent. No, not necessarily. No, they don't have to be linearly independent. All right, so let's try some transformations. Let's think about transformations that might be easy to deal with. Some of the transformations that are kind of listed here are like, reflections, contractions. Contraction is you're shrinking something. Shears, we've talked about shears, and projections, and rotations. So let's do an example where we're doing, let's pick one. What do you want to do? Let's do a reflection, and let's do a reflection about what? The x-axis, the y-axis, another axis. Reflection about what? So let's do a reflection about y equals x, and let's do the reflection on the basis vectors. And if we're going to reflect it about y equals x line, where are we going to take the vector 1, 0?
If that's the point along which we're reflecting, it's just going to go 0 to 1.
Should go to 0, 1, right? And then now let's reflect 0, 1. Where's that going to go? Where? 1, 0. So what's our transformation matrix going to look like? Zero, 1, 1, 0, right? These are just the column vectors. Well, let's give it a try. Did it reflect? Maybe if we extended this.
No,
Let's extend this to go from -1 to 1. times 1 is 1 and 2. Did it reflect? Yeah, looks like it reflected, right? So imagine the y equals x equals y line over here, and then it looks like it did a reflection. So that worked. Let's do another one. We want to reflect, contract. Contract just means shrinking in an x or a y direction. There's a projection. Projection, all that means is, well, the projection is kind of weird because it flattens everything. It makes it go down to one of the axes, usually. Or I guess you could make it collapse into a line, too, that's different from the axis. So which one do you guys want to do? Projection. Did I just sell you guys on projection? Or sold Caesar? Let's do a projection problem. Let's project it onto what? The x-axis, the y-axis, or another line? Another line? What line? Let's try to project it into y equals 1/2 x. This might be tricky. So what are we doing to our basis vectors? So we have our basis vectors. We have our vector 1, 0, and our vector 0, 1. And we want to collapse it onto this line y equals 1/2 x. So that means this vector now has to get collapsed and projected onto this line. So this is the new vector that I want for 1, 0. So the t of 1, 0 has to go to this new vector over here. Can you tell me what the x value is of this t? 1. Well, what's the y value of this t? Half? The angle between the two lines. The angle between the two lines? I don't know if we need that or want that.
Given the sine and cosine, we end up exactly the same place.
No, it has to do with 1/2 x. Yeah. Because if I were to project it, it would just be a. Because I want to know what this point is, right?
We're not used to both the purple and the blue being on the same spot.
Oh yeah, let's put it on a different graph.
We're not used to seeing them the same. We're used to them both being in a different spot, but then they're like right on top of each other. Here they're going to be right on top of each other.
What if I don't know if that helps. So the point 1, 0 has to get projected onto this line, and the projection is like a, unless it's this projection.
Yeah, I think that might be right. You have to add them and end up at 1/2, right?
Now that's going to make it a little bit more difficult. Not impossible. Well, I don't know if I want to figure it out.
We go backwards at it. We say our addition of our vectors is 1/2, and
It might be. So
scratch this.
no, let's see if we can keep working on this. I'm not sure Dylan, I'm not sure I answered your concern. So, can you re-ask the question?
So I was curious why, in my logic, I thought it would be translated as 1 or 2. Why would it be 1 or 2?
Because mapping it to, sorry, mapping it to 1 over 2, you come to would equal d with that. Here is the way that means that's 1
Yeah.
y.
So I think, yeah, this is a 1/2 x, so my line is, the slope is, is this the right slope? I'm getting confused now. Rise over run, so if I rise by 1/2 and I run by 1, so I think this is the right line. And I just had the projection a little bit incorrect, a little bit wrong, but we'll fix that. Still didn't answer your question. Yes, if you have. I thought we were just dropping down to the line vertically, but I don't think this is the correct way to do a projection. I think if we're going to project onto the line, it has to drop in a perpendicular way. And so I need this point where this line drops perpendicular.
Well, you do define the slope of that line and then where it intersects with the point.
Okay, so I think, yeah, you need to find the slope of this line.
Be the negative reciprocal of the slope of 1/2 would be -2.
And then, but I still need this point.
Yeah, and then you add in the point, so y equals to -2x plus b, and then you add in.
So I think this is where Caesar's idea that I said was probably not that important, is to figure out some trig and some angles. All right, let's do a quick trig problem here. This is 1. That's all we know. Damn it.
Need that intersect with your life.
Yeah, so I mean, Susanna's got us going on that, but I thought maybe trig would help. All right, so what's the slope of this line?
Well, I think you can't have a plus b because it goes through 0. Okay.
Well, it has to go through something else, but we have the point 1, 0. Con, you going to save us?
You can use that point.
You can just get the angle.
Wait, let's hear Con's idea and see. Which angle? This one? This one? This one? Oh, theta? Yeah, that's what I thought. But I want this point. So if we have a side,
You
Drop
could just
down.
use a triangle
Yeah,
that's
triangle.
1 and 2, and then you get theta from there, and then you know length of theta.
so the angle should save us, Alex.
Just get a point on the line that the x go over on the direction to. I think we're trying to
And take the arctan of the.
You know a point on the line to
Uh huh.
x.
So we can figure out the angle. Yeah. So the point that we know is this point that we thought was the answer, which is 1, 1/2. And so the arctan of y over x is arctan of 1/2 is 60 degrees, isn't it? Is that right?
So here's your coordinates.
No, it's
Are
not.
you ready for your coordinates?
Yes.
X coordinate 4/5, y coordinate 2/5. I think that's probably that should be exact.
You think that's true?
I wrote out y is equal to -2x plus b. I solved for b, the intercept was root 2. With root 1, and then I set y is equal to -2x plus 2 to 1/2 x.
Uh huh. Okay.
Plug in for x, and the y is equal to 1/2 x.
All right, so if you guys have your ideas, the ones that you guys were telling me, see if you can go through that and get the idea that, see if you get the same result. So what Brian is saying, I think, is that he has minus 2. I think between the slope and the point, you have a y equals this, and then you set them equal to each other. Yeah?
Or better yet, if you know that both vectors use a map to the same point,
They don't. They add to the.
Well, this vector should get mapped to something else. If it was a perpendicular drop over here, it would get mapped to something else.
Would it be, I'm thinking about it, does sine of theta is equal to 1 over square root of 1 plus 4, 1 over square root of 5. Cosine theta is equal to 2 over square root of 5. And then if we treat cosine theta as our new radius, then cosine theta sine theta could be 2 over 5.
And so that's 2 over 5, right?
So now, is this point our transformation matrix?
Yeah. Well, I mean, this is one of the columns for your transformation matrix.
Or 2 of the positions?
So that would be this 4/5, 2/5. I guess if we do the same thing over here, we have the point 0, 1, and then we have the slope here, the same slope, -2, and then we have the equation of this line, y minus 1 is equal to -2, x minus 0. So minus 2x.
So your 0, 1 vector, that's your hypotenuse. On
This one right here?
no, the other.
This one?
Right.
Yeah, if we're going to do trig on it. Yeah? From this blue point, or this? Well, no, I don't know if we need to do that now. All I was interested in is to find this point.
Oh, yeah. So if we know that line is 1 over 2.
Uh-huh.
So we can find the angle, like the angle actually. So
This angle here?
oh no, yeah.
Oh, this angle here?
This angle and we have another triangle, so we can find an angle.
The tricky part is that we want the x and y components of this, and so we would. This is the x. This is the y component here, and this is the x component. And so, if you can somehow find that,
It's going to be x is 2/5 and y is 1/5. Or
that's for the other one.
for the other one.
Yeah. So I think. Like I said, if you could do it any way you guys were thinking of, I think none of those are incorrect. You guys can try to work it out and see, but I believe the answers are going to be 4/5 and 2/5 for this one. And then, did anybody figure out what the next one was? Oh, 2/5 and 1/5. Okay, so hopefully this is the transformation. We'll check it out in a minute. Yeah.
How did you get 4/5 again? You said that equals
Yeah, so set these two equal to each other. 1/2 x equals minus 2x plus 2. And then did some stuff to solve for x.
I got it. Yeah, I did it wrong.
I'm not sure that I did it right, because I'm looking at the results that the first two.
Negative 2, right?
Negative 2.
Negative this.
First,
Yeah.
or it's divided.
All right, well, let's check.
But we don't have our transformation matrix, right?
Well, we do now. We have 4/5, 2/5, and then 2/5, 1/5.
The weird thing is that do they add to 1/2?
I don't know.
Well, we don't, but should they?
No, they don't have to. So let's so 4/5, 2/5. And remember, it's done vertically, right? And then 2/5, 1/5. They all landed here.
It did, but our red dot isn't at 1/2.
So our point would be at 1, 1 here. That landed somewhere.
But if we have the right ratio, it looks like a 1/2 slope. Just a little bit too long. It's probably like.
Notice you can't see that yellow shading either because it all just collapsed into a line. Does it make sense? Does it look okay? We can draw that line just to make sure. That's that line right here. So they all kind of collapse to that line. These 3 points collapse to that line. You can't see it, but the circle also collapsed to that line, and this whole shaded region collapsed to that line. Right? And if we were to try to figure out what this point x was, this is 2/5, 1/5. If you put 2/5, 1/5 in your calculator, it's about, well, it's 0.4 and 0.2, right? Okay? We did it. Yay. Somehow.
Yeah, we definitely transformed it to that line.
Yeah.
We projected it to that line.
Yes.
It didn't come out the way I thought it was going to come out. So
How did you think it was going to come out?
I thought the red dot would be at 1.5.
Well, let's take a look at our matrix. This is not a nice matrix to work with, but let's take a look at that matrix. So, wait, this isn't it.
I think that point actually came out to 6/5, 3/5.
Which one?
The red dot.
All right, so let's see. This is your matrix. 4/5, 2/5, and 2/5, 1/5. And then you want to know what happens to the point 1, 1. Where does it go to? And so this is going to go to, where does it go to? 4/5 plus 2/5 is 6/5, and 2/5 plus 1/5 is 3/5. So it goes to this point. And then, so 6/5 is what, 1.2? And 3/5 is 6.6?
Yes.
So if we trace that around a little bit, we get like 1.2 and 0.6-ish, right? So it is where we wanted it to be. Now, Brian had an interesting question here. His question was, this isn't A, this is X. So the question was, Where did you want it to go? 1, 2?
1 and 1/2.
1 and 1/2. So the question is, whoops, 4/5, 2/5, 2/5, 1/5. So the question is, what value of x sends this thing to 1, 1/2? Right?
I thought we could alter A.
No, we can't alter A because A is it. A is
A's the projection.
A is a projection. So a question would be to try to figure out what this is equal to, and that's something that you should be able to solve for. Dylan? Yeah, it's a system of linear equations solve for x, y, or x1, y1, or x1, x2. All right, we took a really long time doing that stuff, and we need to talk about one-to-one and onto. So we'll talk about one-to-one and onto in our next class and try to review at the same time. So we have an exam on Wednesday. Tonight's the first day of STEM speaker series. After STEM speaker series at the Learning Center, at the STEM Center, they call it a math throwdown. You can go there and study with other people. The math club is holding a big study group. All right, see you guys next time.